For left shift operation, only one variable is sufficient. I have taken just x from this one, whose value is 10, and this is the binary form. Now, left shift the bits by one place. So here you can write any number here that gives the number of places you want to move those bits, shift those bits. I want to shift them by one places. So what does it mean? This 0 should come here. So this should become 0. And this 1 should come here. So this is 1. This 0 should come here. So this is 0. This 1 should come here. So this is 1. And this 0 shifts here. This 0 shifts here. And this 0 shifts here. And this 0 shifts here. Goes on. As it is integer, it is taking 4 bytes, but we are looking at only 8 bits. That is 1 byte. Okay, just to understand it. Now, if you look up to here, this space or this bit is vacant now. So that will be automatically filled by 0. So when you are shifting, one of the bits get vacant. So that has to be filled with 0. So all the bits are shifted by one place. Then what is the result? Let us look at. All these are leading zeros only. So this is the binary number. So how much it is? 1, 2, 4, 8 and 16. 16 plus 4, 20. So Z will get the value 20. So what has happened to the original number? Original number is 10 and we have left shifted by one place. So we got the result as 20. So this means the number is double. Now here this operation is little bit related to arithmetic operation. So when you left shift the bits of any number on the by one place, then it will double the number. Means it will multiply the number by 2. So if you left shift by 2 places, then it will multiply by 4. So as many places that much you are moving, suppose you are moving it by k places, then actual number, your number n will be multiplied by 2 power k. So if you say 1, then it is into 2. If you say 2 places, then it will be 2 square, that is 4. If you say 3 places, then it will be 8. So k places means it is n into 2 to the power of k. So number will be multiplied by this 2 power k as many places as you are moving. So this is little related to arithmetic. So it means if you have to double the number or multiply with powers of 2, instead of multiplying it, just you shift it, then you get the results. That's about left shift. Now let us look at right shift. So I will use the same number, right, same example, just I will make it right shift. This is the binary form of x, that is 1010, and I want to right shift by one place. So let us right shift. So this bit will go here, there is no place, so it is gone. Then this 1 comes here and this 0 comes here, right? At this place we get 1, at this place we get 0. This comes 0 here, this 0 comes here, and this 0 comes here. Now we get left over 1 bit, so this will be filled with 0. All leading bits are zeros only. So what is the number? Here is the number. How much it is? 1, 2, 4. This is 4 plus 1, 5. So Z value will be 5. So what has happened to the number? The original number is 10 and in Z we are getting 5. So number is divided by 2. Yes. If you right shift by one place, it gets divided by 2. So whatever the number is, 2 power 1. If you right shift by 2 places and you say right shift by 2 places, then it will be divided by 4. So by k places if you do, then it will get divided by 2 power k. So remember this one. So if you want to divide the number by powers of 2, so instead of doing it arithmetic operation, you can directly use bitwise operation, that is right shift. Now let us look at unsigned right shift. So for that I will remove this and I will take a different example and I will explain right shift, unsigned right shift. Suppose number is minus 10, negative 10. So first of all, let us know how it is represented in memory, because negative numbers are represented in 2's complement form. Alright, so let us see how it is represented. Actually 10 means 1010. These are the bits that are defining a number. Then leading bits are all zeros. So actually it's an integer. If I take 4 bytes, it will be too lengthy. So let us understand it at a byte level. So let us add 4 more leading zeros. This is 1 byte. Then we have to make it as minus 10. So first of all, find 1's complement, right? 1's complement. So every bit is inverted. So this becomes 1 and this becomes 0, 1 and 0, 1, 1, 1, 1. This is in 1 byte, right? Now next is 2's complement. For 2's complement, add 1 to this 1's complement. So 1 plus 1 is 0, carry 1, and that 1 as it is. This is 1 and 0, 1, 1, 1, 1. This is the 2's complement of 10. So this is nothing but minus 10. This is minus 10. So minus 10 is represented like this. Alright. I am showing only 1 byte, right? Just for understanding it. So if you look at this most significant bit, it is 1. It is 1. Now upon that x, suppose this is x, right? It is minus 10. So x is minus 10 and it is 1, 1, 1, 1, 0, 1, 1, 0 in 1 byte. Now if I say x right shift by 1, then what happens? This 1 comes here, this 1 comes here, and this 0 comes here, and this 1 comes here, right? This 1 comes here, this 1 is here, and this 1 is here, and this will be 0, and this 1 remains as it is. So remember this, when you perform right shift by 1 or any places, the sign bit is untouched. If the number is negative, sign bit is untouched. Leave. But if you want to include that sign and treat the number as unsigned, then you have to use right shift including the sign bit by 1 place. Now what it becomes, instead of this, we get the number 1, 1, 0, 1, 1, 1, and this 1 comes here, right? This 1 comes here, and this bit will be 0. This is what the number becomes. So when this became 0 means this is a positive number. Yes, if a negative number, if you perform unsigned right shift, then it becomes a positive number. Let us see what the number we got. This is 1, 2, 4, 8, 16, 32, 64. 64 plus 16, that is 80, and 32 plus 8 is 40, 40 plus 80, 120, 120, and this is 2 plus 1, 3. So this is 123. So we got the number as 123, and this is positive 123. So the difference between right shift and unsigned right shift is, in right shift, sign bit is untouched, it remains negative only. And that will be, if it is in untouched means this is 2's complement only. If you want to see the correct number, actual number, take the 2's complement of this one. But here the number became positive and it is positive 123. Now the last operation left is not. Let us look at not. So for that I will take just one value and I will show you here. X is, this is the binary form, X is 10. Now if I say Z assign not of X, so not of this has to be stored. So not means what? Every bit is inverted. So this becomes 1, this becomes 0, this becomes 1, 0, 1, 1, 1, 1. So this is the result in Z in binary form. And I am taking only 1 byte, again I am telling you. So now how much it is? Because this is sign bit as per a byte, so this has become a negative number. So what is the actual value? So you have to take 2's complement to know the actual value. So let us find out the 2's complement of this one, so we can know what is the result of this one. So I will write down 2's complement. So first of all I take the number as it is, then let us find out 2's complement. So for that, first of all, this is Z value, right? Form 1's complement. 1's complement means all the bits are inverted again, right? So 0, 1, 0, 1, 0, 0, 0, 0. So we got back the same thing, yes. But 1 is added to this one to get the 2's complement. So 2's complement, we get it like this. 0 plus 1 is 1, and this is 1 as it is, 0 as it is, 1 as it is, 0, 0, 0, 0. I'm not working on this one right now, right? See that Z, you forget it. On 1's complement, I have added 1. So I got this result. So this is in the positive form. So what is the value? This is 1, 2, 4, 8. So 8 plus 2, 10 plus 1, 11. So this is 11. So actually this is 11. But this is sign bit. So this is minus 11. Minus 11. Yes, if you take integer also you get the same thing because all bits will become 1. So when you take 2's complement again you get back the same number. So one thing you can observe here that if any number is there, if you take its not negation, Then if it is a 10, it will become minus 11. It means if it is a 6, then it will become minus 7. So this is one thing you can observe. So that's all about all the bitwise operations. I have explained you all the bitwise operations. So you can work out this by yourself once, then you get used to with them. Now if required, this will be useful for you. Otherwise, these are definitely useful in interviews. And about academics, this may not be there in your theoretical paper, but it may be there if there is a viva voce or oral examination. Right? So knowing about these operators will really helpful for you. So just you need to practice this once, do it by yourself once, then it is easy, you can remember it. Just if you watch them, they looks very scary, looks very difficult. No, they are damn easy, just do it by yourself once.